Hello, everybody. So what we're going to be covering today is arc length, or the length of a curve. So I think this is going to be an easier to understand topic than the previous topic of solids of revolution. So hopefully you'll like this. So the concept is very simple, right? So let's see here. So the concept is this. So suppose you have a curve, which I'm going to draw now. All right, so there's a curve. Um, if you took that curve and you straightened it out, right, then it would be a little bit longer than it shows here, right? Like, so let's just say that these are numbers here. 1, 2, 3, 4, 5, 6, 7, 8, right? So you can see that, on the x-axis, the curve is 6 units, right? Why is it 6 units, right? Because it goes from x equals 2 to x equals 8. Right? But that's not the actual length of the curve. Um, because if you were able to, like if that curve was a piece of string and you were able to straighten it out, it would be longer than 6. So, but that is not the length of the curve. Uh, if you could, which of course, you can't, it's just a picture, but if you could, straighten out the curve, it would be longer than 6. Also, let's just do this on the y-axis too while we're doing this. So we have 1, 2, 3, 4, 5, also 6. So 3 to 6. So this original curve here, if I can, I was going to, magic of computers, I can duplicate this, duplicate, come over here. Um, through the magic of computers, we have uh, something that doesn't work. That is 3. This is 6, right? But if you straightened out the curve, straighten curve, it would look something more like this, right? How long? Don't really know, right? I just know that number one, I don't know how to spell long. Trying to put a question mark there. But we want to know how long that is, okay? And if you could straighten it out like that, then that would be the arc length. That's what we call the arc length. And that's what we're trying to calculate in this section, okay? So if we can figure that out, so if we can figure out the length, then that is what we call the arc length of the curve. Okay, so it's a pretty simple concept. Now, how are we going to do it? Well, we need to derive that. Okay, so let's derivation of formula. So this is not the derivation of the formula that's probably in the book. I didn't look at the book, but I never really see anybody do this. But the idea is this. So we know that you can use an integral to sum something up, right? So if you have a curve like this, so we got, a y-axis, we have an x-axis, and then we got a curve. Okay, and I'm not even going to like label that curve with what function it is or anything like that. I'm just going to say there's a curve, right? Because integrals, or not integrals, I don't want to start with an integral. What I want to say is that, so to estimate this length, you could pretend that your curve was actually made up of a lot of small line segments. You could estimate the curve as, you know, some number of line segments. Now, what would that look like? Well, what that would look like is if we took this curve here, duplicate it like this, and instead of what we have here, we're going to put like this. Just a bunch of little tiny straight lines like that. If we did that, then the sum of the line segments would be approximately the sum we were looking for. The sum of the length of the line segments is approximately what we want. Right? It's not exactly what we want because, of course, the line segments that I drew in pink are not um, are not exactly where the curve is, right? They're close to the curve, but they're not the actual curve, right? So that's the curve, and those are the line segments. But if we could add up all of those lengths, then that would be what we want. So let's actually do that. So we could do that as follows. We could add up the length of the line segments. So suppose each, actually, let me just copy my picture again. Sorry. Duplicate, come down here. All right. So what we want to actually do that. So what we're going to do is we're going to say, suppose each line segment had a length. And we're just going to call those lengths for now, like delta x1, delta x2, delta x3. No, we're not. That's delta s. We want to call it s, sorry. Delta s1, delta s2, delta s3, and so on until you get to whatever the last one is, which will be delta sn. So each of those has a length now, because I said so. That one's delta s1, then delta s2, dot, dot, dot. And you get to the end and you have delta sn. So there you go. If we do that, then what would the length of the pink curve be, right? Then the sum of the line segments is, what is it? So it's going to be a summation like this. We did n of them, so we'll go 1 to n, and then we're just adding up the delta si's, whatever those are. And that's not great because in terms of how we're going to calculate this, because what is delta si, right? Delta si is nothing. It's the length. Oops, I deleted it. It's the length over here, but we still don't know how to calculate that length. So just because you said, the length is the sum of the lengths, and you don't know how to calculate any lengths, then we haven't done anything, right? But we could. So this is going to be the uh, arc length is not this. It is approximately this, right? Because the pink and the blue lines are different lines, and we're adding up the pink right now. So that's okay. So we have the arc length is approximately this. But here's the thing: if we if each line segment can be written in terms of x and y, we can do something with that. But each line segment can be written in terms of x and y. Using the Pythagorean theorem. And it's not even hard. If you got, so the idea is this. So each line segment, right? So like, let's just call this delta S. It's just a representative one of them. If you think of this as being there's some horizontal change and then there's some vertical change, right? And we could call the horizontal change delta X, and we could call the vertical change delta Y. And if we do that, then there's a relationship between these three things, and that relationship is going to be the Pythagorean theorem, right? So we each line segment can be written in terms of x and y using the Pythagorean theorem. Of course, you know the Pythagorean theorem, right? A squared plus b squared equals c squared. So for us, what that's going to look like is delta x squared plus delta y squared equals delta s squared, like that. Okay? And that's getting somewhere, because then what we can do is rewrite our arc length in terms of that x and y. So arc length, which is approximately equal to the delta si's from 1 to n, is now going to be from 1 to n of, oh, we didn't actually solve this. One moment here. So let me move this up all just a little bit, like that. And so the thing is if you want delta s, which we do, then you're going to have to square root both sides here. So you're going to end up with square root delta x squared plus delta y squared is going to be the delta s. Okay, and it's not going to be plus or minus delta s, by the way, even though we square rooted, because delta s is the length of a line. It's not ever going to be negative. Okay, so delta s is always positive. So there's no need for like a plus or minus on the outside or anything like that. It's always a positive number. So come back over here, and we are going to basically just substitute this in for all of the delta s's, which means just basically we're going to put square root symbol, and then we're just going to go delta xi squared plus delta yi squared. Okay, and that is your formula. It's not the arc length, it's almost the arc length. Okay, now from here, there's kind of ways to rewrite this depending on whether you're going to do an integral or whether you want to do an integral now, or whether you want to do some algebra and then do then change it into an integral. So it doesn't really matter which it is. So I think what I'm going to do is just kind of do the integral now, which is a little bit hand wavy. So this is kind of, this part isn't, super rigorous that I'm going to do, just letting you know. But basically, to make the arc length equal instead of approximately equal, we need to use infinity line segments, right? So what we're going to do is, let's see, let the number of line segments go to infinity. Because if we do, then it will become a perfect approximation because there won't be any difference between the curve and the line segments if they are infinitely small, right? So what we're going to get then when we do that is that the arc length now is going to be equal, not approximately equal to the limit as in goes to infinity of this, which I should have just duplicated. I'll duplicate it now. Boom. Okay. So if we can do that, then that would be what we want. And we've seen a few times, and this is why it's not going to be super rigorous here, that when you let this go to infinity, right? Words hard. The n goes to infinity. Each of these delta xi's and delta yi's is going to get smaller and smaller, right? Because just from the picture, if the delta s is shrinking in length so that we can fit more of them on the curve, then if delta s gets smaller, delta x gets smaller, delta y gets smaller, and what happens is we're going to start writing these when they become infinitesimally small. We're going to write them as dx and dy instead of delta x and delta y. We've seen this before, and we haven't, you can't go through the math every time you do it here. But this is going to turn into an integral. The sum turns into an integral. The deltas will turn into d's. So you end up with dx squared plus dy squared is what we end up there with. And then your limits of integration are going to be on your curve. And it's going to be basically what are the limits of integration? Well, they're where you're starting and where you're ending. They can be in x or they can be in y, depending on the problem. Okay. And so I'm just going to put for now a and b and then a little comment about those. So we have a and b, and I'm just going to say the formula is not ready to use yet. Right? You can't just plug something into this formula. But the limits of integration will eventually be in terms of whatever variable you end up using for your integral. Of the variable you use to integrate. Over. Okay. So this formula here is a good thing to remember, but it is not like the actual formula that you use. So you can make it into the formula that you use with a little bit of algebra. So let's do that. So let's turn the formula we have. Or use algebra to make the formula useful. Okay, so here's the idea. So I'm going to do this not with the integral here. I'm just going to do this with a without the integral symbol. So let's say we have dx squared plus dy squared. I can put those in parentheses. I'm not going to. So there's an algebra trick here. What you can do is you can say, I want to factor out a dx squared. Now you can't do it. Actually, you know what? That's not what I want to do. Sorry. I changed my mind just now based on Nothing. There's just more than one way to do it, and I just changed my mind mid-sentence about how I wanted to do it. So here's what you could do. You can rewrite this as dx squared plus dy squared over, and then I can write this dx over dx. Now, of course, I haven't done anything here, right? Because I multiplied by dx over dx, which is 1, so that's fine. This is the same as this. Now, what you can do after that is you take one of these dx's and you put it in the denominator. So it looks like this. So you got your 1 dx there, and then 1 dx there. Okay, now what you can do then is you can say since dx is actually the square root of dx squared, as long as dx is positive, which it is. Now, why is it positive? Same thing from the picture here, right? Our picture, all of these were lengths. The delta s, the delta x, and the delta y were all lengths, which by definition are positive here. And so, even after you take the limit, then they have to be greater than or equal to 0. So that's fine. So there's no plus or minus or anything to worry about here. So dx can be written square root of dx squared. So then you can take this formula, you can take this bottom one, and you can put it into a square root. Sorry, just having trouble getting a highlighter. You can put it into a square root. So you have dx squared plus dy squared over dx squared square root. And then you still got this dx out there. Okay, almost. So then now you can take both of these square roots and put them into one square root. So now you have dx squared plus dy squared over dx squared. And then you still got this dx hanging on the outside. Great. Almost. Then you could take this right here and you can split up this fraction into two fractions by writing it dx squared over dx squared plus dy squared over dx squared with the dx on the outside. And then now you can cancel here. Dx squared over dx squared is 1. And dy squared over dx squared, we're going to write that as dy over dx squared. Dx. Okay, and that's the form that we want. Now, there's a derivation that is actually a little bit more rigorous than this, where we basically calculate this using using a derivative by relating these using the slope of the curve, right? Because like the slope of the curve is dy over dx, and you can relate this to dy or to the derivative directly, and then from here you actually have the derivative built in from the beginning, as opposed to what I did where I'm just kind of pretending that it's here at the end. If that didn't make sense to you, that's fine. I'm just pointing out that there's better derivations of this, and I did this one for a particular reason. The reason I did this one is because our formulas for arc length are easy to see here, because I can write this now. We can say, there are several, not, I was going to say many, but I don't know about that, several formulas for arc length. So here are some of them. So arc length is going to be, it's going to be an integral from a to b of this thing that we just calculated, 1 plus dy dx squared dx. That's the one you're going to use most often. But thing is that if you didn't want to do an x integral, you wanted to do a y integral, you could have. All you would have to do is go back here to the beginning of this derivation, and instead of doing dx over dx, you would have done dy over dy. Everything would have been the same, except that like your x's and y's would be reversed here. So you do this first one if your curve is a function of x. So this is if your curve is y equals a function of x, basically. And then a and b are in terms of x. Okay. But if you had redone it with what I said, where you can reverse the x and the y's, then your formula would be dy over dx. No, that's what we just did. Dx over dy, and then a dy integral. And you would use this if you had your curve as like x equals g of y. Now, you don't normally have curves written in terms of y, but if you do, you can use this. And if you do, then your limits need to be in terms of x. And maybe just to make it clear that these are different, I'll use different letters here, C and D. So that looks the same. All we did was we changed the x's and the y's around. And there's even a third one that you could do if you know parametric equations, which we don't at this point, but I will mention it just in case, because you may see it in next semester or in Math 4C for sure. So, or even if you have parametric curves. Now, what a parametric curve is when you have like a third variable. So like x is some function of t, so like f of t, and y is also some function of t. So they're both functions of t, and you know t has some range. I'll just go back to a and b. I don't care. If your curves are parametric, then your arc length could be still an integral from a to b. And again, you go back up to here and you replace this dx with dt, and then you go through this entire process. And when you get to the end, nothing cancels because you have x's, y's, and t's. And so what you end up with for your integral is an integral that looks like this. Dx dt squared plus dy dt, oops, the y squared dt. I'm going to rewrite that because it's unreadable. So you could even end up with that. So I don't know if we're going to use both the x and the y formulas, or we're just going to use the x formula. But we're definitely not using this third one that's up there right now. So just keep that in mind. So for the homework, you are only using the first one, and maybe the second one. What happened? Oh, I think I did the first, I did the second one twice. Let me go back up here and grab the correct one. Come on. There you go. Okay, so depending on whether you want to do an x integral or a y integral, and I say depending on whether you want to, but you don't actually have a choice. So just keep that in mind. So let's look at some examples. So the way these problems work is they give you a curve, and then they ask you to set up an integral. So here's an example. So let's say find the length of, can I do this? Sorry, I'm trying to think of an integral we can do. Um, these are actually tricky here. Hold on. We're not going to find the length. I'm going to write out, also, I would say, write an integral to find the length of y equals, actually, I don't want to call it that. I want to say f of x. F of x equals, now this could be any curve. Now, in theory, it could be any curve. In practice, it can't be because we won't be able to we won't be able to solve the integral. So I don't like that. Hold on, I'm changing it. 1/4 x squared from or over the interval. We're just going to go, let's say, -1 to positive. That's fine. Okay, so what's going on here? So the idea is you have your curve. So your curve is just a curve. So if I go 1, 2, 3, 4, -1, -2, -3, and here I want to go 1, 2, 3, 4. Okay, so think about this. This curve is just a parabola, so easy to draw. And I know a couple of points on the parabola I could figure out. It goes through 0, 0. If you put a -1 in, you get a quarter. All right, very small. So down here. And if you put a 1 in, oh, we already said that, you get a quarter. If you put a 2 in, you get a 1. And if you put a 4 in, you get 4 squared is 16. 16 over 4 is 4. So you have a little curve like this. And that's your curve that we're looking at. Okay? And what we're trying to do is find that length. So we know the length is the arc length formula. So of course we know this. Arc length equals integral from a to b, integral 1 plus dy dx squared dx. That's an x. Okay. So that is what we want to do. So what do we have to do? We have to figure out the dy dx. Basically, that's the only thing that's hard. So dy dx is just the derivative of the function for the curve with respect to x, right? So if you have f of x equals 1/4 x squared, which is what I have, right? Yeah. Right, that's the same as, you could also just say the curve is y equals 1/4 x squared, right? So dy dx is just the derivative. So dy dx, or f prime of x, whatever you want to call it, is just the derivative of this function. So you're just going to take the derivative of 1/4 x squared. So derivatives are easy. So we just do the power rule for derivatives. So the 2 comes down in front. Looks like we're going to have 1/2 x, right? So that's your derivative. The limits of integration are, well, what should they be, do you think? If we're going to integrate this in terms of x, then of course they're going to be right here, the -1 and the 4, which in terms of x, right? So -1, +4. So your arc length integral is simply going to be an integral from -1 to +4. That's easy. Square root, and it's 1 plus dy dx squared. So you just fill in the dy dx, which you just calculated as the derivative of the curve. So you have 1 plus 1/2 x squared dx. And this would be the answer because all I did was I asked you to come up with the integral. Okay. Now, something you have to be aware of is that these integrals are often very difficult to solve. The square root makes these difficult or impossible a lot of the time. So like this one right here, -1 to +4 square root, if you square this, you're going to end up with 1/4 x squared again. That's just chance. That's not indicative of anything important, that it looks like the original function. This integral is impossible for us until halfway through Math 4B. Right? So you got to be in the middle of calculus 2 before you could even make an attempt at that integral. So it's there. Now, having said that, if you just need a number, then that is what Wolfram Alpha is for, things like that. Because of course, we can just go here and then we can just say integrate, we got a square root, 1 plus, it was quarter, it's going to write 1.25 because it's easier to type in that way, 1/4 x squared, and then dx from -1 to 4. So you see it gave me my integral. It gave me the picture too, by the way. Oh, that's not the picture of the curve, right? This is not the curve. It's the picture of the function that is in the integral, which is not the original one. So 6.956. 6.956. 6.956. So that's a computer answer, not a person answer, because again, we can't do that integral. So it's about 7. And does that make sense? It does make sense that it's about 7, right? Like this is from -1 to 4, so this length is 5. You know it's bigger than 5 because it's curved here. But you know how much bigger? Well, it's about 7. Okay, so those are the types of integrals that we're looking at. Now, the thing that I boxed here, the integral before we did the integral, that's the actual answer that you would be typing into the computer. So you don't have to answer this one by typing into a computer. Consider the curve, find the arc length. Oh man, so this is going to be rough. Okay. So this is going to be, I think we'll do this one to give you an idea of the terribleness that they give you in the homework, and so you can see something important here. So in this one, we have a curve. The curve is f of x equals 1/6 x cubed plus 1/2x. And then our interval, we want the length over, I'm not writing it the way they did, 1 to 4. That's for the x. X in. Okay, there you go. And they want, we need the actual length as an exact number. So we do actually have to do this integral. All right, I'm not going to graph it. I'm just going to go straight to the work here. So we know we need the derivative, right? So so we know we have y equals f of x equals, what is it? It is 1/6 x cubed plus 1 over 2x, which I'm going to write 2x to the -1. Yeah, that's fine, actually. That's not the best way, right? So step 1, we need the derivative. We need dy dx, or your book always uses f prime, so that's why I'm writing both here. We need dy dx or f prime, which are the same thing. So we need the derivative. I guess I'll write dy dx. It's the derivative of this function. Now the derivative's not hard. You need to remember derivatives. So bring the 3 down in front. So 3 over 6 is a half. Subtract 1 from the power. So we get 1/2 x squared. Here we need the derivative of 2x to the -1. That is going to be chain rule. Bring the -1 down in front. So -2x to the -2. And then you have to multiply by the derivative of what's inside, which is 2, for the chain rule. So what we have is 1/2 x squared plus, this is actually a minus because of that minus there, minus 2 over 2x quantity squared, which is 2 over 4x squared, which is 1 over 2x squared. Okay, so this is what we get there. Okay, now you're going to take that and you're going to put that in the integral. So the integral that we need to solve is going to be, we know it's right, it's an integral from a to b square root 1 plus dy dx, which we have, squared dx, and we just calculated the dy dx. So we have the integral from a to b square root 1 plus parentheses, right? This is dy dx. So that all has to go in here. 1/2 x squared minus 1 over 2x squared, and then dx on the outside. And this is the integral we have to do. And their claim is that this is going to kind of just work itself out here by magic. So do lots of algebra. Sad face. Or, and I'm not recommending this, or you type just the stuff in the square root, skip the square root, just the stuff in the square root, type that into Wolfram Alpha, and it will spit out a nice answer probably, and then come back here. But if we do it by hand, what we're going to have to do is, number 1, FOIL this out. So multiply this out because it's squared. So you're going to have to FOIL it. So 1/2 x squared times 1/2 x squared is 1/4 x to the 4th. Then 1/2 x squared times 1 over 2x squared, right? So that's, I need to write it like this so we can see x squared over 2. That's the first one. And then 1 over 2x squared. So when you multiply these together, you're going to end up with 2 and 2 on the bottom. If you multiply these, if you multiply those, you end up with x squared on the top and 4x squared on the bottom. The x squares cancel and you just have a quarter. But then you get it twice. So you end up with a half. So you end up with a half. And then when you multiply this by itself, you end up with, looks like going to be another plus 1 over 4x to the fourth. Okay, so you multiply that out however you do, and FOIL it out. Then you combine your like terms because you've got 1/2 and a 1 here. So that's a 3/2. So, oh, oops, I made a typo here. Sorry, I didn't think about it. But when you multiply this times this one's plus and this one's minus. So the result would be minus. So this should be a minus 1/2 here. And again, you probably have to do that yourself. Otherwise, you're lost because I just scribbled over here. All right. Now this right here and this right here are like terms. So combine them. So when we do that, we end up with 1/4 x to the fourth plus a half plus 1 over 4x to the fourth. And then a dx. Okay, so you end up with all that. And like I said, these integrals are almost impossible to set or to work through. One thing I do want to do is I should have put my a and b in here. What are the a and the b? Going back to the beginning of the problem, they give to us, right? They're 1 and 4. So I should have just put those in from the beginning here. 1, 4, 1, 4, 1, 4. Okay, now this right here is something that you should start to recognize because this is a very common trick on these types of problems. I'm going to rewrite this. This is x to the fourth over 4 plus a half plus, I'm going to write this one. Well, no, I'm just going to leave it the way it is. And what you might look at this and recognize that there's some kind of pattern here, right? There is some kind of pattern to notice. Okay, and the pattern is going to be this, is that if you write this, it's x to the fourth over 4, but you could write that as x squared over 2 squared, right? And the 1/2, just write the 1/2 as 1/2. And the 1 over 4x to the fourth, you could write as 1 over 2x squared, like that. Okay? And this is actually it factors. It's a perfect square trinomial, believe it or not. Right? What I mean by that is if you do a plus b squared and you get a squared plus 2ab plus b squared, like that, that's what's going on over here. And so if you type this in, like x squared over 2 squared, like if I go to Wolfram here, it does help just to, be willing to use your tools. You can factor it by hand, it's possible, it's just a pain. So if I type in x squared over 2 parentheses squared plus 1/2 plus 1 over 2x parentheses squared, like that. If I type this in, I'm not doing the whole integral. I'm just doing, the part in the square root. And it tells me the result, but, oh, something happened. Oh, I got to redo this. The 2x down here should have been in an extra set of parentheses. Right. If you look at the 1/2 x squared, look where the x is, it's in the wrong place. So I need parentheses here. There we go. So that looks correct. No. It's supposed to be, I made another typo here. So let's fix that one. Not looking good for me. Okay, I think that's finally typed in correctly. Um, so then should be able to do something with it. And the thing you should be able to do with it is what did they do? Hold on a second. Yeah, I mean, I guess you would want to take that last one, but man, okay, I don't like the way they did it. Okay, forget Wolfram Alpha. We have to do it by hand. Um, so, what would you do here? Well, basically, it's just what I saw, um, or what I said over here. It's this is the pattern: a squared plus 2ab plus b squared. So if you just um, check that uh, if the a is x squared over 2, right? According to comparing this to this, and the b is 1 over 2x squared, that 2ab is supposed to be what? So if you work out 2ab is 2x squared over 2, and then 1 over 2x squared, which is 2x squared over 2, 1 over 2x squared. Cancel, 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 cancel. So x squared cancels with x squared. 2 cancels with the 2. And you're left with just, it looks like a half. And this right here is the middle term over here. In our integral. That's the middle term in our integral. Okay, now what's that mean? What that means is that we have it in this form, we could write it in this form. So we rewrite it as the a plus b form because it actually is that. So we can come here, we have the integral from 1 to 4. A plus b would be x squared over 2 squared, no, sorry, x squared over 2 plus 1 over 2x squared, like that. And you might think like, okay, well, what did that get us? Well, what it got us was the fact that we now have a square and a square root up against each other, and so they can cancel. So the point if you have a square root of a squared, I shouldn't use an a square root of something squared. So like, I don't know, z would just be z, right? They cancel. So you cancel the square root and the second power. This is a terrible second problem. So you end up here. Okay. Now all of this work for simplifying this integral was to get it to this point where you could recognize that it kind of looked something like this: a squared b squared 2ab, a squared b squared 2ab. just so you could rewrite it like this. So to go from here to here, that was so you could cancel your square root and your second power, which means no square roots or powers here. I mean, there's that power, but no overall power. And then this integral is now finally doable. So now finally, we can integrate. Now that's like I fully admit that the algebra you have to do there sucks. And that's just the way it is. So let me rewrite this the way I want to do it. So let's write this as 1/2 x squared plus 1/2 x to the negative 2. Because this integral here is now easy, the one that we have. So you're just going to use power rule. So you find an antiderivative. So x cubed over 3. Antiderivative, right? We did a derivative earlier in the problem, but now we're doing antiderivatives. So now add 1 to the power, divide by the power. So x to the negative 1 over negative 1, from 1 to 4. This is x cubed over 6 plus, minus, looks like 1 over 2x, from 1 to 4. Put in your 4, put in your 1. 4 cubed over 6 minus 1 over 2 times 4. Minus, put in your 1. 1 cubed over 6 minus 1 over 2 times 1. 4 cubed is, 64? So 64 over 6 minus 1/8 minus 1/6 plus 1/2 when I get rid of all my parentheses. So 64 over 6 minus 1 over 8 minus 1 over 6 plus 1/2, and please be the right answer. I get 87 over 8, and that is the correct answer. So that's good. And you had to do this by hand. I mean, or just type it into Wolfram Alpha from the beginning. Because the decimal will not be accepted in the computer. So required for Newton. Okay. So that's going to be it for this video, but I'm going to do another video with more examples of this so you can see this algebra again, because this was difficult. All right, so that's it for now. Talk to you guys later.